In our previous video, we defined several terms related to spherical mirrors. What are spherical mirrors? Mirrors in which the curved reflecting surface forms a part of a sphere are called spherical mirrors. Spherical mirrors can be of two types. One in which reflecting surface is curved inwards, they're called concave mirrors, and the others in which the reflecting surface is curved outwards, they're called convex mirrors. The center of the reflecting surface is called the pole. The center of a sphere of which they form a part is called the center of curvature. And the radius of that sphere is called the radius of curvature. CP here is the radius of curvature. Note that for a concave mirror, the center of curvature lies at the front of the reflecting surface, whereas for a convex mirror, it lies at the back of the reflecting surface. Okay, I also told you that the midpoint of CP is called the focal point of the respective mirror. The other name for it is principal focus. It's called so because it lies on the principal axis. Okay, let's just remove the convex mirror for a while and concentrate on the concave mirror for now. Now this focal point of a concave mirror is a little more than just a midpoint. It's also a point where all the rays of light parallel to each other as well as to the principal axis converge after reflection. Let's try to understand this statement in detail. Let's take the sun as our object. Why? Because I want only parallel rays of light to be incident on the mirror. And the rays of light from the sun can be considered to be almost parallel. But why? Being a sphere, sun emits light radially outwards. That is, rays of light travel outwards along the radius. But we know that the sun is at a very large distance away from the earth. Hence, the rays from the sun coming towards the surface of the earth are considered parallel. So our object, which is the sun, is present at infinity, and it's emitting parallel rays of light. We know that all the rays of light after being incident on any surface will follow laws of reflection. We see that after reflection, each ray is indeed following those laws. Angle of incidence is equal to the angle of reflection. And all the three lie in the same plane. Where are they going after reflection? Well, they are all meeting each other at the principal focus. Yes, they are all converging at the principal focus. And this is where the image of an object is formed. Yes, this is an image of the sun and it's a real image. Now, if you project this point of convergence on a piece of paper, the paper at that point will start getting hotter and will eventually catch fire. As the bulk of rays from the sun are all concentrated at one single point by this concave mirror, the temperature at this point rises. And it's too much temperature for a thin piece of paper to withhold. Similarly, instead of a sun, we can take any other object kept at infinity. And the rays of light from that object incident on the mirror will be parallel to each other. So we saw that if the rays of light are parallel to each other as well as to the principal axis, they will always converge at the principal focus. And this is true for any other object as well. Now I would want to mention one thing here, that this does not depend on the position of the object. Yes, it does not only work when the object is at infinity. No matter where the object is kept on the principal axis, if the rays of light incident on the mirror are parallel to each other as well as to the principal axis, they will always converge at the principal focus. What if the rays of light are parallel to each other but not parallel to the principal axis? Where will they go in that case? Let's find out what happens then. Suppose that the rays of light are incident on the mirror. As you can see, these rays are parallel to each other but not to the principal axis. These rays will be reflected in such a way such that the laws of reflection are obeyed. You see that here also all the rays are converging. But here the point of convergence is not the principal focus. Instead, it's a point above the principal axis. This point is called focus as all the rays are focused at this point. It's not called the principal focus, because it does not lie on the principal axis. So we define focus as a point where all the parallel rays converge after bouncing off from the reflecting surface of the concave mirror. It is the principal focus if it lies on the principal axis. And it will only lie on the principal axis if the rays of light are parallel to each other as well as to the principal axis. What if the light rays are passing through the principal focus? Yes, it means the light rays won't be parallel. Consider one light ray from a point on the object passing through the principal focus and is incident on the mirror. We know that this ray will be reflected according to the laws of reflection. Consider two more rays from different points of the object, both passing through the principal focus, incident on the mirror. After reflection from the concave mirror, we see that they all travel parallel to the first reflected ray. So what can we conclude from this? If the rays of light pass through the principal focus and are incident on the mirror, then after reflection, they travel parallel to each other. And this is true for any position behind the principal focus. But what if the object is kept at the principal focus? Well, in that case also, all the rays will travel parallel to each other after reflection. I want to discuss one important point before I end this video. In reality, every object emits rays of light in all possible directions. Or to be more specific, from any point on an object, infinitely many rays of light travel in all the possible directions. But then, where will the image of the object be formed? Is it formed on the principal focus again? In the coming videos, we will learn the characteristics of images formed by concave mirrors.